on to the third demo. This one we call Lifting the Curse of Rarity, Smarter Testing for Safer AVs. And I'm going to do, the sort of 5 minutes of intro, and then I'm going to hand off to Dr. Haowei Sun, who's the co-founder of SaferDrive AI, a startup. And Dr. Chun Gao is going to be joining us remotely from University of Toronto. He's currently transitioning to University of Michigan, but he also has a partial appointment with NVIDIA that he's going to retain when he joins University of Michigan. And you'll see heavy leverage of the NVIDIA toolchain in this demo. So let's talk about safer AVs. We did a full hour-long panel on this yesterday at the Symposium. So that will eventually be on our YouTube channel, and people can check that out for the deeper discussion on this topic. But one of the things that we were really trying to get at in the panel discussion yesterday was, right now, this idea of how safe is safe enough, that's a decision that's being made by AV companies, right? They decide how safe is safe enough. And that seems problematic, right? Because you look at this list of other people who want to know how safe is safe enough, and who probably have every right to have a very strong opinion about how safe is safe enough, right? So the general public obviously wants to know, right? They're going to have to decide, like in the previous demo, they're going to have to decide, should they step into the crosswalk in front of that AV or not, right? And so knowing how safe it is an important thing. They're going to drive next to that AV, like we showed in the previous demo as well. But they also might be inside the AV, right, as robotaxi users. So, this clearly is something that the general public's very interested in and needs to know. Public safety advocates, obviously in their role of understanding risks and benefits and advocating for safety, need to know. Regulators who issue the permits need to know. When it gets to litigation, the judicial system needs to know how to decide fault and assess liability. Insurance companies need to figure out how to underwrite the risks, but also give credit for the benefits. AV companies themselves, are interested in some standards because of the fact that when things go wrong, it's buffering to your reputation to be able to say that you aligned to a set of industry standards, right? So there's value to the AV companies. Mobility providers, this could either be, vehicle manufacturers who release autonomous vehicle features on their vehicles, or it could also be mobility services like Uber and Lyft who might have autonomous vehicles in their mobility fleets. And of course, investors who provide the lifeblood capital that allows AV progress to continue also want to know. So it's a very important question for us to address. And typically the way engineers approach safety, these sort of two pillars of safety, the way I think about it, on the left-hand side you have safety by design, and what that really means is, the engineers sit down, decide what kind of feature they want to deliver into the world. They decide what the requirements for how that should function are. And then they go through a process using things like functional safety or safety of the intended function, where they actually go and imagine all the ways it can fail and what hazards would those failures create. And then they put in place countermeasures in their design to deal with those hazards. So there's a whole side that's just about how do you make a safe design, and there are firms out there that audit that kind of safe design performance. What we're really talking about in this demo is going to be what's on the right-hand side there, the safety validation process. And so this is once the engineers have done the design and now you need to prove safety, how do you prove safety? And the first one listed there is testing versus known risks, right? So that's what normally happens, has happened in industry forever, where you take a scenario catalog of all the known hard scenarios, the unprotected left turns, the two-lane roundabouts, merging on freeways, parallel parking, all the sort of known scenarios that are stressful. or have safety risks, and you test your vehicle in those to make sure it meets your performance requirements. The thing that we're really going to discuss in this demo here is the second one, which is this discovering unknown risks. So even as good as engineers' imaginations are in that design phase of how the design might fail, there's going to still be, in the chaos of the real world, other failure modes that exist, right? And so there are unknown risks out there. And so the only way to find those out is to put that vehicle with its AV system out into the world and see how it behaves. And what we're going to show you is a way to do that in simulation. And the reason for simulation is because physical testing, when you're trying to decide whether to launch your vehicle, you need really high mileage, and simulation scales and physical testing does not scale, right? And so Dr. Henry Liu put out a great paper in Nature. If you type cursive rarity into Google, it'll be the top link. It's well worth reading. And it contains this chart, where if you look at the black line, it says the really sort of high occurrence stuff is normal driving, right? It's really easy to train an AV to handle normal driving. The harder part is when you get down that curve into the more rare events and the near miss events as well as the accident scenarios. You see accidents there at 10 to the minus 6. So those are 1 in a million type events, right? So that's where physical testing doesn't scale, right? If you have to drive 1 million miles to document one accident scenario, that's just not going to work. But you can do it in simulation. And the real good news is that the sim to real gaps are closing amazingly quickly. And that's what's going to really be what we'll be demonstrating in the balance of this demo. And again, you'll see all of the sort of tool chain that we've been developing in this transition to a digital proving ground that NSF has been enabling in their funding of MCity2. You'll see that demonstrated in the tool chain that we use here. So the specific use case that then I'm going to turn over to Haowei to discuss is, if we're an AV company and we want to deploy an AV into a certain city, how do we do an AV behavioral safety assessment at city scale? And specifically, how can we use the latest state-of-the-art generative AI techniques to create these simulation worlds and to populate them with the edge cases to really test the robustness or lack of robustness that the AV has? So with that, I'll turn over to Haowei to take it from here.
Yeah, thank you, Greg, for the introduction. So what I'm going to talk is essentially the core part of MCity. So we have an open source simulation platform, we call it TeraSim, in which we are duplicating MCity from the real world physical world into the digital world. And this raises our question is that, what if we can extend from one single MCity to anywhere in the world? So that's about the inspiration of what I'm gonna discuss today. So let's start from one single thing is the world coordinate. So just give me a longitude and latitude, like for example, roundabout in Ann Arbor, highway on Arizona, or something like that. And we will do 4 steps to recreate this digital proving ground from scratch, all automatically. The first step is that we are generating the HD and 3D map utilizing generative AI from satellite map. And the second step is that we have all the static environment in step 1, and we are adding dynamic elements like vehicles, pedestrians, cyclists, etc. And they are interacting, behaving in the simulation just like they are doing in the real world. So that's what we call the naturalistic driving environment. The third step is we are translating this kind of abstract scenarios into the language that autonomous vehicles can understand. It's called sensor simulation, including surrounding cameras and LiDARs. And the last step is that we have all the things we need, and we want to really bring about some challenges, some corner cases to stress test the autonomous vehicle to see if it is robust and stable under like endless real world challenges. And the output, we are aiming to provide this as an end-to-end autonomous vehicle testing ground. So we'll start with step 1, the generative AI HD map generation. So the HD map generation itself is time-consuming and manual labor expensive. So, but let's get started with one single point from Ann Arbor, the roundabout. It's very close to here. I think that's just a 4 to 5 minutes drive from where we are at now. So this is a normal roundabout in Ann Arbor. And the next step is that we got satellite image and aviation image from different vendors. So this is what we got, the satellite image, and we utilize the advanced generative AI models, the image editing and generation models to directly give us the road network from that. So you can see the road topologies, the lane shapes. It aligns perfectly with the real-world satellite image, and we are translating this into multiple formats, including OpenDrive, Lane2, which is commonly used in the autonomous driving simulation and the autonomous driving stack itself. So we got the HD map already. The next step is that we are adding naturalistic driving environment into that. So every single dynamic elements here, we are trying to control and generate it. So left-hand side is an example about the basic methodology we're using. This is a paper we published in 2023 on Nature Communications. It's about how we utilize neural network to mimic the real-world human beings' driving behavior. So this is another roundabout in Ann Arbor. It's located in the south part of Ann Arbor. It's probably the most dangerous roundabout in Michigan as well. So we have roadside cameras to capture and record the real-world trajectories in the left-hand side. And you can see what we can do is that we pre-train our neural network with large-scale naturalistic driving data set to provide nearly identical traffic environments at the right-hand side. So you can see we capture all kinds of complex and subtle interactions, including the yielding behaviors and other things. So it's even indistinguishable from the real-world collected trajectories. And coming back to our roundabout here, we are generating the background traffic participants in this exact roundabout. So you can see this is a couple of different vehicles running inside this roundabout. And also the neural network-based traffic agent simulation is just not limited to one roundabout. Actually, we can do it in the whole Ann Arbor. So you can see this is the bird eye view of the whole Ann Arbor. And then we zoom in, zoom out to different like intersections, highways, ramps, roundabouts, and something like that. We are seeing a continuously evolving and interacting city-scale digital twin. It can run for hours of running long time. So that we can provide a really thorough and complete stress testing environment for autonomous vehicles. Like we can finish a round trip from the north side of Ann Arbor to the south side of Ann Arbor with like a half-hour drive in congestion environment or something like that. So this is what naturalistic driving environment can bring us about. So the third step is what we mentioned is all about trajectories, object level informations, and the next step is a sensor simulation where we will translate this kind of information from our perspective view to the autonomous vehicle's perspective view. So with here, I'll hand it over to Jim. Jim, can you hear us?
Can you hear me?
Yeah, I can hear you.
Oh, nice. So hi, everyone. I'm Jun from the ECA department at Michigan. So basically what we need to do in this component is that we need to simulate the sensors for the simulate sensor input for the autonomous vehicles. And the key goal we want to achieve is that what these vehicles see in our simulator should be the same as what they see in our real world. So next slide. So in particular, in this case, we focus on RGB simulation because the RGB cameras is always the most commonly used sensors in the autonomous vehicles. On the left side, we first provide the driving environment that generated using the process that Haowei has talked about before. And this driving environment provides information of the road layout and also the behaviors of each other cars on the road. We will also provide a street view images to indicate the style of the road that we want to generate. For example, in this case, we want to generate a roundabout on the Ann Arbor city. But on the other side, we might need to generate images, not in Ann Arbor, but maybe in some places like San Diego or Paris or somewhere. With this two input, we can then fit this into NVIDIA Cosmos Drive, a video foundation model that is specifically trained for generating realistic RGB videos on the right side. By combining the load net traffic and also the street view image, our model is able to generate realistic RGB image on the right side, and we can feed these RGB videos to autonomous vehicles for testing and evaluation. And then next one, beyond only generating the front cameras, we can even further extend it into the 360 surrounding video cameras so that when we are driving, the car is not only able to see what's in front of this car, but also what's on the sides, left, right, or even what's on the back of this car, so that we can make a full decisions of what the current driving behavior should be. Combining all of this, we are able to generate a holistic sensor input for autonomous vehicles purely using the generative AI that we developed. Next slide. So here is the overall pipeline. We can first extract the load map, adding the traffic using the process that Haowei developed, and move the viewpoint into the cars that we want to drive, and then generate the final RGB videos to as what we are showing here. So next one. So after introducing all of these three components, from how we can generate the HD map to generate the driving environment and finally curating these sensor simulations, we are now ready to stress test our autonomous vehicles, since everything here is generated by AI, and we can control what we want to generate so that we can curate the corner cases for stress testing the autonomous vehicles. So next one. Yeah, yes. So specifically, in this case, we are interested in several types of stress testing, especially for the corner cases that are rare to see in our real world and also safety critical for autonomous vehicles, like Greg has mentioned in the beginning. We can do 4 types of rare cases generation. First is static adversity. We can add stored vehicles, construction zones, etc. onto the load by adjusting the HD map. We can also change the behaviors of the cars, such as adding the unprotected left-turn cars into the HD map, so that we can simulate this kind of vehicle adversities. We can also do weather simulation to change the environment of the RGB videos that we want to generate. Because in this case, we can utilize this generative AI. We can utilize text to control what we want to generate in the final RGB videos. And in this case, we want to do some changes, such as changing from the sunny days into the snowy or foggy days that we are commonly see in Ann Arbor. Lastly is VRU adversity, where we want to add unsafe pedestrians into the load, such as the jaywalking. So next one. So here is one result. In this demo, on the left side, we are showing the same layout input to all of the videos. On the right side, we can change the weathers. Like, for example, we have sunny days, rainy days, like snowy days, or even foggy days. We can also change the daytime. So we have this for example, we have the nighttime here. We can also have the daytime here. We can also change the colors of the vehicles. For example, there are some black cars. They can also be like the red cars or white cars. All of this showcase the opportunities for us to curate a large scale of diverse data set for stress testing the autonomous vehicles using this generative AI. So next slide is another example where the incoming black car is failed to yield in the roundabout. And this is achieved by generating the driving environment on the left side and feed this generated environment into our generative AI for RGB final generation. So next one. So more broadly, our pipeline is not just applicable to the Ann Arbor use case. We can scale it out to any places in the world. For example, in this video, we add a pedestrian crossing in Paris. On the front view of this car, we can see the pedestrians is crossing on the road, and the ego vehicles, the autonomous vehicle that we are driving, needs to stop and wait for these pedestrians passing across the road. For the next one is we can also do aggressive merging in Germany. For example, in this case, the gray car in front of the ego cars is trying to merge into the lane very aggressively. We can also try to drive on a highway in Arizona, such as doing the zigzag on the highway. And next one is like in San Diego. the left black vehicles in this video is running a red light, and the eco car needs to stop to avoid the crash, even if the eco car here is facing a green light. So in this one, we can also go to Chicago, where in this case the white car is trying to merge into the lane, but it's not supposed to do such a merge because it's very dangerous. And the eco car also must react to this dangerous merge from the white car. By combining all of this, everything we have presented here has already been open sourced, and with the code and also paper for every researchers in the community to reproduce our results. And you're also welcome to try if you're interested. Thank you. And we're happy to take questions.
All right, we are open for questions.
Yeah, thank you. Fantastic. First, I want to say what's inspiring about this is also to see, research at the University of Michigan spinning out into a startup, right? Demonstrating the kind of innovation and entrepreneurial spirit that comes out of this effort. So I think that's worth highlighting. Yeah. My question is this. It's very cool to see the generation of environments from different parts of the world with their different features. And then there's the other module that's generating the vehicle behaviors from the naturalistic data. So we could see the different environments from all over the world. That's very visual. But I'm curious about the naturalistic data that you're using to drive the generation of vehicle and other agent interactions, because in different parts of the world, as you know well, the way these agents interact on roadways varies a lot. So I'm wondering if you could just say something about what data you're using and how much you can represent that, or what data you would need, or how easy that is to do.
Yeah, so that's a very good question. Let me get back to the NeuroND part maybe. So essentially we are trying to we know that in different cities, actually human beings drive very, very different. Like in Ann Arbor and in New York, that's definitely different cases. That's the reason why we're using, why it's not working? Yeah. So that's the reason why we're proposing this kind of what we call the NeuroND part. So it is pre-trained on large scale real world naturalistic driving data, but it can also be fine-tuned with location specific data. So for example, for one single city, our estimate is that we need around 100 hours of the naturalistic driving data to let us fully mimic the local driving traffic patterns. And also, we are not just generating the behavior level of simulation. We are also taking the information of the traffic itself. Like, is it a congested environment, like the morning peak hours or the evening peak hours? Because we have vendors that can provide this kind of information. We see that in the navigation, like Google Map or something like that. So this kind of data is also utilized in our construction of the traffic environment.
Thank you.
Thank you.
So you talked about your, the generative AI pipeline. And so can you talk a little bit about, the time if you were to choose a location to where you've kind of combined both, both tools, the NVIDIA tool and your tool? How long does that all take? And what is the level of expertise needed to even utilize those tools? Can you, do you have to have very clear subject domain expertise, or can you have more generalized expertise in order to build a simulation out like this?
Yeah, like currently what we have, like in these 4 different steps, the major thing is actually the Gen AI sensor simulation, because that's where we utilize the video generation model. And normally for one thing we see in the demonstration we need around 10 minutes on one single H100 graphic card to do that. And with all the open source code we provided, we are foreseeing currently we still need some expertise in terms of fine tune the video generation model, because it's very general. It might be utilized for the movie generation or something like that. It's not specialized for autonomous vehicles. So we need some sort of this fine tune techniques to really help us generating domain specific data. But with the rapid evolvement of generative AI, we're already seeing these barriers coming lower and lower. And we hope that one day, like you just have the data and you're good to go. So that is our current status. And we are also seeing the efficiency being very much improved over the past couple of months. And we are seeing a couple of video generation models that can already decrease the generation time from like 10 minutes to like 10 seconds or something like that. And we are actively integrating this kind of technique as well. Okay. So we are seeing this is easier to use and faster, hopefully near real time in the short future.
Okay.
Yeah.
Yeah, and you saw one of the slides at the end that Jun presented was that all of this has been published open source, right, with papers and a GitHub repo. But also, you know, Haowei has spun out a startup, right? And part of what Haowei will do is to help people customize that, right? If you're busy in industry and don't have time to allocate to that, you can easily work with Haowei startup to get that work done. You know, and Haowei, I guess, you know, you touched on the rate of change in the generative AI world. I mean, maybe you could just sort of give a feel from your perspective, because to me, it's just mind-blowingly fast, right? I mean, there's a whole amount of effort that needs to be put into just how do you stay on the cutting edge of that wave like Jun and Haowei are, right? But maybe give your perspective on that, the rate of change of Gen AI.
Yeah, I see it as, that's a very good question. I see the generative AI is like exponentially increasing. So I've been using this kind of video generation model for a while. I remember in the last year, I was trying this, like, not to say like we have surrounding cameras, even in one single camera, you can see the sky and the building, the color and the shape is constantly changing over time. It's just like in your wildest dream that could, you know, that's what we generate. But within just half a year to 1 year, we are seeing this very impressive photorealistic and super consistent generative AI result. And we are seeing this being faster and faster. So yeah, that's kind of like the newest generative AI technique, really like it's mitigating a lot of things that we can never imagine before. So yeah.
And maybe Jun Gao, maybe you could give us your perspective also, given your expertise on this topic.
Yeah, actually, I want to echo the point from Haowei. Actually, the progress of video generation has been very fast in the past years. But actually, I also want to point out, it's like, actually, if we compare video generation versus the language model generation, because like language model, we have seen the ChatGPT moment, or GPT-3, and even for now, GPT-5 something. But to me, what I see in the video model generation is actually we haven't not yet reached the ChatGPT moment. Because the model we have been seeing, for example, the model we have been using here is only a 7 billion model compared to language model, we have like hundreds of billion parameters. There's a huge model in language and a huge data set that we have in language. Video model is not there yet. So I would imagine in the next several years, we are going to see even better performance video generations, and then even better performance and also better quality, much faster video model coming out.
Other questions? Okay. Thank you, Haowei. Thank you, Jun.